This is Thermal Energy Processes by Fasse, Jericho, Amberlynn, Adam, and myself, Mitchell. Today, we are going to dive into thermal energy-based machining processes. Unlike traditional machining, which relies on physical tools cutting into the material, these processes use intense heat, whether from electricity, lasers, plasma, or electron beams, to melt or vaporize material away. This especially is useful for hard or brittle materials that are difficult to cut with machining tools, or for parts that require extreme precision. Common examples of these processes include electrical discharge machining, or EDMs, laser beam machining, LBMs, electron beam machining, EBMs, and plasma arc machining, or PAMs. Throughout the presentation, here's what we will be covering. We'll start by understanding how thermal machining works in general, then go through the four main types of processes in detail. We'll also look at the pros and cons of each, see how they're used in real-world industries like aerospace or automotive, and talk about how these processes are evolving. Lastly, we'll wrap up with the takeaways that'll help you decide which method is the best for each job. The core idea behind all thermal machining processes is the same. Apply a highly concentrated source of heat to a specific region of the material until it melts or vaporizes. This could come from an electrical discharge, a laser beam, an electron beam, or a plasma arc. Because there is no physical contact between the tool and the workpiece, there is no tool wear and no mechanical force exerted, making these processes great for delicate or hard to machine components. The key advantage here is precision, since only a small, localized area is affected by the heat. The rest of the part remains mostly unchanged.
All thermal machining processes share some key features. First and foremost, they use heat, not mechanical force, to remove material, which is why they don't rely on cutting edges or tool pressure. This allows us to machine very hard or brittle materials that would normally fracture under traditional methods. Another benefit is that there is no tool wear because there's no contact. This means better dimensional control over time. Since both of these processes are highly focused and controllable, they're often used for high precision or micro-scale parts, and many are integrated into automated or CNC-based systems. Thermal machining methods have been around for almost a century and have advanced dramatically over time. The earliest form, EDM, was developed in the 1940s by Soviet scientists to shape hard materials using spark erosion. The invention of the laser in 1960 opened the door for laser machining, initially in microelectronics and medicine. By the 1970s, electron beams were being used in high-precision aerospace components. Plasma arc machining followed and became popular in the heavy industrial sectors like shipbuilding. In recent decades, the rise of CNC automation, CAD/CAM integration, and AI-driven systems has pushed thermal machining into ultra-precise and efficient territory. These processes are now key in everything from aerospace to micro-scale medical tools. Now we'll go over the four main types of thermal machining processes. First is EDM, or electrical discharge machining. It removes material using electrical sparks between an electrode and a conductive workpiece. It's great for precision work like dies and molds. Next is LBM, or laser beam machining. This uses a focused laser to cut or vaporize material. It works on both metals and nonmetals and is commonly used for microdrilling and electronics. EBM, or electron beam machining, is similar to LBM but uses a stream of electrons inside a vacuum chamber. It's extremely precise, especially for aerospace and micro-scale application. Finally, PAM, or plasma arc machining, uses a jet of superheated ionized gas to cut through thick metals. It's fast and powerful, often used in industries like shipbuilding. Each method has its own strengths depending on the material, precision needed, and production goals. So, how does electrical discharge machining actually work? It uses a soft electrode to generate a controlled spark between the electrode and the target surface. This spark creates intense localized heat, enough to vaporize or melt tiny amounts of material, without the tool ever touching the part. EDM is known for doing things traditional machining can't, either because the geometry is too complex or the quality requirements are too tight. Some common uses include drilling very small holes, producing molds and dies, and even removing broken drill bits from expensive parts. It also creates clean, burr-free components, which are especially useful in medical and aerospace applications. Real-world examples of EDM-produced parts include pacemakers, turbine blades, and automotive components like valve lifters and manifolds.
Here are some advantages and disadvantages for electrical discharge machining. Some advantages include that it can be used to cut complex shapes, deep holes, and more importantly, undercuts, which cannot be machined with other conventional methods, so EDM is more reliable with those processes. It does not create burrs when cutting, it does not leave marks, the process is not affected by the hardness of the material, and there is little to no force needed when operating, therefore, you can eliminate the possibility of human error. Some disadvantages include that you cannot remove large amounts of material quickly, so if you are manufacturing something that is time restricted, EDM is limited to those restraints. It is an energy intensive process, which means that it can be harmful to the environment and leave a carbon footprint. It's an expensive operating cost and it's limited to conductive materials only. Next, we have laser beam machining, which utilizes the concentrated power of laser beams to achieve precise material removal. Now, there are a variety of laser types for laser beam machining that are each used for specific reasons. This includes CO2 lasers, which are more suitable for cutting and engraving a variety of materials, ND-YAG lasers, which are ideal for applications that require deep penetration and precision, and fiber lasers, which are used for fine cutting and engraving applications. Now, some real-world examples of LBM would include electronic boards, wire stripping, tattoo removal, hair removal, and surgical procedures, which include tumor removal and cataract surgery. And all of these examples show the importance of precision and accuracy that LBM is able to provide. Here are some advantages and disadvantages for laser beam machining. Some advantages include the high precision, that there is no material contamination, it uses a high speed, a variety of materials can be used with LBM, and a variety of applications and industries use LBM machining. Some disadvantages would include the limitations on material thickness. Laser interaction with certain materials can produce hazardous fumes, which would require proper ventilation in areas that are using laser beam machining. There is also a high energy consumption with LBM, which also creates a carbon footprint, and there are upfront costs when using this machinery. Next, we have electron beam machining, which is a narrow beam of high-velocity electrons that are directed toward the workpiece that creates heat and vaporizes the material. An important note for electron beam machining is that it's used for producing very small-sized circular holes, and these holes are only circular. Some real-world examples of EBM would include custom implants in the medical industry, some complex molds and die, specialized components for nuclear reactors, and in the aero industry, some lightweight and strong parts for aircraft engines.
Continuing off of what my colleague said, let's talk about electron beam melting's advantages and disadvantages. One of the biggest advantages is its high accuracy and high repeatability, meaning its ability to produce the same part to spec every single time. Electron beam melting also has a better surface finish compared to other thermal cutting processes and also leads to no distortions. Since there is no physical contact being made with the workpiece, there is no force needed or tool replacement required, which saves a lot on cost and physical distortions. The disadvantages, however, are that it produces hazardous X-rays, which are very harmful for the operator. Therefore, the machine is operated in an enclosed space and therefore requires very skilled operators to work it. And the operator also is not able to see inside the machine as it is operating. Only electrically conducting materials can be machined, so this means a lot of regular plastics and ceramics are not applicable for this process. The equipment cost for this machine is very high since it's such a specialized type of machining, and it also needs secondary backing or sacrificial materials to function. Let's talk about a different kind of machining now, plasma arc machining. The way plasma arc machining works is that a gas is heated up with an electrical arc between the electrode and nozzle, and this gas is heated up to the point where it is ionized and becomes plasma. This plasma is then shot out through the nozzle at very high speeds, which melts the metal. Now, when the metal is melted, the high velocity of the stream causes the metal to be displaced and therefore be machined. Some real world examples of plasma arc machining are profile cutting, and they're often used on really hard to machine materials, so like cast iron or stainless steel. Let's talk about some disadvantages and advantages of plasma arc machining. So some of the advantages are that it can cut different types of metal materials since it's based on melting and not conductivity. It's also much cleaner since it's not reacting, it doesn't use any chemicals, it is just a simple melting process. It requires a lot less maintenance than the other types of thermal machining processes and requires less energy to conduct operations. Again, since it's melting based and not electron based. The disadvantages are that it's complicated to use. This is very common, as we've seen, for these types of specialized devices. And this is not ideal for larger jobs, just naturally due to bed space or just the volume of the enclosure, and also due to its comparatively slower speed. The gas fumes and high temperatures that are involved in this kind of machining can also be very damaging to the workpiece depending on the type of material used. When choosing which thermal machining process to use, there are several key factors to keep in mind. First is material type. EDM and EBM only work with conductive materials, while LBM and PAM can handle more variety. Then there's precision. For very tight tolerances, EDM or LBM is a better choice. Part geometry also matters. EDM is great for complex internal features, while PAM is better for cutting profiles. You'll also need to consider the size and thickness of the part. Some processes like LBM struggle with thicker materials. Production volume is another factor. High-speed options like PAM are ideal for batch production, while EDM is better for low-volume, high-precision parts. Finally, think about cost, energy use, and safety. EBM has high setup costs and X-ray hazards, while PAM produces fumes and requires good ventilation. The right process depends on balancing all of these factors for your specific job.
Thermal machining processes are used across a wide range of industries because of their precision, versatility, and ability to handle tough materials. In aerospace, they're essential for making complex parts like turbine blades and cooling holes. Medical devices such as implants and microsurgical tools often rely on EDM or LBM for their small, intricate geometries. In automotive, EDM and PAM are used for parts like cylinder heads and valve lifters. The electronics industry uses LBM and EBM for micro drilling and printed circuit board production. Meanwhile, tool and die making heavily depend on EDM for cavity shaping. In the energy sector, especially nuclear, thermal machining is used for handling high strength and heat resistant alloys. These processes also widely are used in military applications where precision and performance are critical. Let's compare the four main types side by side. EDM requires electrically conductive materials, offers high precision, but has relatively slow cutting speeds. Laser beam machining can handle a wide range of materials, both conductive and non-conductive, and is excellent for fine detail. Electron beam machining also gives extremely high precision, especially in micro applications, but only works in a vacuum and with conductive materials. Plasma arc machining is the most aggressive of the four. It's very fast and great for cutting thick materials, but it has a lower precision and rougher finish. Choosing the right method depends on the material, accuracy needs, production speed, and cost constraints. While thermomachining is extremely useful, it comes with serious environmental and safety considerations. For instance, laser and plasma processes emit harmful fumes and gases, so proper extraction systems are necessary. Electron beam machining must be conducted in a vacuum chamber and produces X-rays, so shielding is critical. EDM uses high voltage and immersion in dielectric fluid, making electrical safety and proper grounding essential. There are also heat and fire risks, especially with combustible materials nearby. Operators must wear PPE like heat-resistant gloves, hearing protection, and safety glasses, especially in LBM and PAM environments. Lastly, proper disposal of fluids, electrodes, and consumables helps reduce environmental impact. As manufacturing continues to evolve, so does thermal machining. One of the biggest trends is increased automation. Machines can now self-optimize in real time using AI and machine learning. Hybrid systems are also becoming popular, combining EDM with traditional milling or additive processes for faster, more flexible workflows. Another key focus is on sustainability. Companies are moving toward low-energy lasers, eco-friendly dielectric fluids, and emission control systems. At the same time, miniaturization is expanding. Thermal machining is being pushed into the micro and nanoscale, especially for things like biomedical stents, sensors, and microfluidic devices. And of course, with Industry 4.0, thermal machines are becoming smarter, using cloud connectivity and sensors for predictive maintenance and system optimization. To summarize, thermal machining processes rely on intense localized heat to remove material, making them ideal for hard, brittle, or complex components. We covered the four major methods: EDM, LBM, EBM, and PAM, each with unique strengths. Choosing the right method depends on factors like the material's conductivity, how precise the cut needs to be, and whether speed or accuracy is more important. These processes are incredibly powerful, but also come with safety and environmental challenges due to heat, radiation, and emissions. Looking ahead, thermal machining will continue evolving with AI integration, hybrid techniques, and eco-friendly solutions, making it a critical part of advanced manufacturing going forward.